Hi, welcome to this video series on Diffie-Hellman parameter generation and testing. We have been talking about the properties of group generators and how do we test a particular element as a generator of a group. Today, I will continue that discussion, and my focus is to um, present you an algorithm. The algorithm will actually test whether a given element is a generator of a given group. It's a difficult problem in general, so I'm going to specialize it for a particular scenario. The scenario I'm going to talk about is that if you know the order of the group, then the problem is much more easier to solve. Okay, so let's get straight into the theorem that will be the foundation for our discussion in this session. There is a wonderful theorem. It says that if you have a group of order q, don't confuse this q with the q that we used in safe prime definition. Just assume q is some number; it need not even be prime. Okay, let G be a group of order q, and let's assume you're given also the prime factorization of q, meaning if you multiply all the prime numbers p1 to p2 pk, you will get the number q back. Okay, and there is only one unique prime factorization anyways for a given number. Okay, and then what you're going to do is you are going to ignore for example the first element of your prime factorization. The trick you do is basically you take your prime factors, multiply it, right? Multiply all of the prime factors to obtain the q, the order q. You take order q and divide it by pi. So how do we get q1? Q1 is nothing but q by p1. Q2 is nothing but q by p2. So essentially you leave one element at a time. Okay, and what is the theorem is saying? The theorem is saying this: an element is a generator if and only if g power qi is not equal to 1 for all 1 less than or equal to I less than or equal to k. Meaning if you take your g and raise it to the power q power I, right? And if you don't get 1 for all of your factors, then you know for sure your element G is a generator. That's basically what the theorem is saying. And how is this going to help us in detecting the fact that G is a generator or not? It's straight away applicable, right? As soon as you know your G, and as soon as you know your group order and the prime factorization, you can apply this theorem because it's an if and only if condition. Okay, so I encoded this into this little Python code. I would like to warn you that I probably have not tested the Python code for all corner cases. For example, if the factors are not prime factors, the theorem is not applicable. And I have not really tested that whether the given list of factors actually have that property. Okay, I do have some basic assumptions. For example, I check whether the element the element G for which we are checking whether it's generator or not satisfies some basic group properties. You know, G power order is 1, and if you multiply all the products of the factors, you get the order. And of course, there is at least one factor and so on. So some very basic checks I have done here. And let me explain the for loop now. The for loop is basically same as the theorem that you're seeing here, right? These two lines of the theorems are actually encoded here. What I'm doing is I go through each factor, right? The prime factors that you're seeing, P1, P2, Pk. And then I check whether G power order by factor is 1. Of course, we are working in a finite group. That's why I have to use the modulus, right? And if you find a 1, that means what can you say? It means that G actually is generating a subgroup, right, of this particular order, right? That means G cannot be the generator of the original group. So we can return false immediately. So after we tried all the prime factors, if none of the factors is satisfying this condition, then we know for sure the original element G must be generating the group of a given order. Okay, that's basically it. That's the whole idea of this Python code. Okay, so I'm going to run it and show you some examples. The program will ask for the generator and the modulus and the group order, and of course the prime factors as well. If we feed in all of these, it can tell us whether the element G is a generator or not. So what I'm going to do is I'm starting with some simple examples first, right? And then I will dive into the details one by one. So let me generate a simple group first, okay? Let's see, we know for sure Z star 11 is a cyclic group, and we can apply this theorem now straight away. So what I'm going to do is I'm going to apply this theorem now on simple generators. Like I will first import from my is generator test, import all the functions, and I'm going to call the run function, which is the kind of the main function. It's going to ask me what element you want to test for. Let's say 2. Is 2 a generator? Let's check that. Modulus is 11. Of course, the order is 1 less than the modulus, but the reason I asked for the input is that the theorem is applicable for other groups as well, not just the multiplicative group, okay? Of prime order, prime groups. You can apply it for other orders as well, okay? Order is 10 in this case because the modulus is 11. What are the prime factors of 10? 2 and 5. And now the program says 2 is a generator, which we can confirm here. 2 is a generator, okay? Let's do the same again for other cases. Let's say, what about number 6? We know for sure 6 is a generator. Let's check that. Yeah, 6 is also considered as a generator. Very nice. So let's move on to something negative. Let's try. For example, we know for sure 3 is not a generator of the entire group. So we will put that here, and we try. Okay, 3 is not a generator, as we can see. What about interesting cases like subgroups? Let's take a simple scenario. Let's take 9. 9 is actually not a generator of this entire group, but it does generate a subgroup of order 5, right? We can see here it generates a group of order 5. Okay, so how do we test that? We can plug in GS9, modulus is still 11, order is 5. Let's see whether we can check this. What are the prime factors of 5? I mean, it's only 1. 1 times 5 is 5. So 5 is the prime factor. And it confirms that 9 is a generator. Okay. We can take a counter example. Let's take a negative example. For instance, let's take, okay, well, I can't take 3, 9, 5, 4, 1, right? 3 generates 5, 4 also generates 5, 9, and 1 is useless anyway. So let's take 8, okay? We do know for sure 8 is not a generator of a subgroup, right? It generates the entire group. Okay, let's try that. Let's see whether we can find a problem here. Yeah, it says assertion failure right away because first of all, some of the basic group rules are not followed, right? The group rule is that G power order must be 1. That must be true for any group, independent of whether it's a cyclic or not. Okay. As a matter of fact, we can now actually apply the same theorem for non-cyclic groups. Okay. So let's try some kind of group which is non-cyclic group. Okay. Or actually, more precisely, let's try something other than ZP star. You know, we have been playing with Z11, Z13, and so on. Let's try for a composite number. Okay, let's try for 15. And we know for sure this is not a cyclic group. I talked about the theorems earlier. This is not a cyclic group, but it does have cyclic subgroups. Okay, for example, it does have a cyclic subgroup generated by number 7, right? What can I do with it? And can I test whether 7 is a generator of a subgroup of order 4? Okay, let's do that. So what I'm going to do is I'll do this run. It's going to ask me what is the generator you want to test for, 7. What is your modulus? Is still 15. What is the order of the group? Is 4. What are the prime factors of the order? It's just 2, right? 2 into 2 is 4. So hopefully it will say that 7 is generating a group, rather a subgroup of order 4. Let's try that. What did I do? I made a mistake because I didn't repeat the order 2 times 2. So remember here I'm checking for the product of the order is factors is equal to order. So let me run it again. 7, 5, 4. The prime factors are actually 2 and 2. That assertion checking actually requires me to repeat the prime factors. If I didn't have that assert, I don't have to do add the duplicate elements. Anyway, it's just a small error handling thing, which is good because I can now demonstrate that 7 is indeed a generator of the group of order 4, because we can see here. Okay. If you know how to compute the Euler torsion function for 15, you would quickly say it is the group order is 8. So we must have subgroups of order 2, order 4. So that's clear. And if we now go back to this theorem that I talked about earlier, the generator testing theorem, right? What is interesting is that, let's zoom in here. What is interesting is that this theorem is actually coming more or less straight from the Lagrange's theorem that we talked about, one of the Lagrange's theorems. In his theorem, he says like this: the order of the group, right, is divisible by order of the subgroups. Okay, that's basically the core of the proof. I'm not going to show you the proof for this, but that's essentially the idea that is built inside in this theorem. And equivalently, the Python program actually does this basically. Again, if you know the prime factors, it is easy to check whether a particular element is a generator, the prime factor of the order of the group. Okay. Of course, if you are working with, say, ZP star, it's much easier, right? ZP star, the order of the group is p minus 1. So modulus is basically 1 more than the order. But my program is a generalization of the ZP star context, so we can apply it for other groups as well. If you wanted to apply it to elliptic curves, then you have to define the meaning of multiplication, right? Here I'm using the Pow function because it's regular multiplication, and there you have to change the meaning of multiplication by point addition and whatnot. Okay, anyway, that's not necessary for this discussion, but I just want to add the fact that this is a general theorem applicable for all groups. You could apply to test whether element is generator or not.